Hello everyone and welcome back to the channel. Today we are continuing with the KiCAD tutorial series. This is the second part of video number 6. In this video I want to show you the essential steps that you need to take for finalizing your schematic before you move on to the PCB design. These steps will make sure that we're not jumping into the PCB layout without ensuring that our schematic is rock solid and without errors, and also making sure that we have considered everything properly. Now, learning to design beautiful circuits, schematics and PCBs is only part of the journey. If you want to bring your designs to life, you need PCBWay. PCBWay is a high quality manufacturer of PCBs and they can assemble the PCBs for you as well. The order process is very simple. You upload your Gerber files and they will give you a quote very quickly. One of the things I really like about PCBWay is their shared projects, which is a community-driven platform where makers can share their electronic projects with other people. I also share my projects here, so if you ever wanted to order one of the PCBs that I've designed on video, you can do that through PCBWay and their website. So again, a huge thank you to PCBWay for sponsoring this video and making this content possible. Now back to the video. In this video, we'll cover the complete process of finalizing a schematic in KiCAD, taking it from a drawn diagram to a state where it's fully prepared for the PCB layout. So this isn't just about making the PCB or the schematic look good, it's about ensuring that it's accurate and it's complete. And if you're going to look at the schematic at a future date, you want to make sure all the information that you considered during the design is there. So we'll start by making sure all our component values and specification are correct. Then we'll move on to annotating our components, which is crucial for identifying them later. We'll also look at adding net labels and power symbols for clarity, which we've looked at briefly in the past as well. Of course, we'll perform a thorough electrical rule check or ERC check to catch any potential errors. A key part of the process is assigning footprints to our components, so I will detail that as well. We'll also generate a bill of materials or BOM, which is essential for ordering parts. And finally, we'll briefly touch on things like test points and saving the project. We want to double check all the connections that we've made in the schematic. Now this might seem repetitive, but it's so important it deserves its own section. Double check all your connections. Even a single incorrect connection in your schematic can lead to a non-functional PCB obviously. So it's much easier to fix these errors now in the schematic stage than later when you have a physical board in front of you, or when you've been halfway through your PCB design, realizing you've missed a connection and then having to redo a lot of the PCB design just to correct it afterwards. So pay close attention to where wires connect to component pins. Make sure there are no accidental disconnects or short circuits. KiCAD uses junction dots to indicate where the wires are connected. So you can see those junctions with these dots here. If you see a crossing without a dot, that means that those wires are not connected. So that's something you have to be careful with. So try not to have them, but let's say you have this something going like this, then this connection is not connected together. For checking connections, zoom into the critical areas of the schematic to get a close-up view, making sure it connects to the correct pins. Use the highlight net feature in KiCAD. To trace the connections. So in KiCAD, you can highlight nets by pressing the button above the tab button. I'm not sure what it's called, but next to one. So you can see it highlights everything connected to there. Now, if I was to connect the 3v3 line to somewhere else, let's say we connect it over here and we press that same button again, you can see this net is connected to this net over here, and we can try that on the 5 volt and the VBAT as well. So you can see all the VBAT is highlighted in purple. Now, if you're using purple for one of your net highlights, then that might get a little bit confusing, but it's a very handy feature to make sure that all your nets are connected properly. We can also make sure that our connections from this page of the schematic is going to our other pages. So you can see 3v3 over here is also connected. I ignore this pink highlight because I'm using that color for a design rule. Now, something that can help with making sure all your connections are connected properly is running an ERC check on your schematic. So to run an ERC check, you basically need to click this button over here and then click Run ERC. Now generally this will give you a lot of errors. So you can see I've got errors and warnings. So I've got 11 errors over here. And it basically says that my ground pin is not driven by any output power pin because ground is a power symbol and it needs to connect to a power pin. The same thing also applies for VBAT. Some of them you can ignore, so I'm going to ignore all the ground ones because I don't need that connecting to an output pin. To resolve that, what you can do is change your battery connection, let's say, to a ground output, or you can change the pin on the USB-C connector to an output. So to show you how you would do that, basically, let's say we go into here, we edit the symbol. So in the symbol, you can see that the ground pin has a passive electrical type. Now you can change that to a power output, save that. And if I go back to my schematic, go back to my ERC rule checker and delete all the markers and run the ERC check again, you can see that the ERC errors on the ground have disappeared. Now let's quickly go through the other ERC errors to make sure that we haven't got any errors that we are not happy with. So I've got some errors in here that say that my symbol doesn't match the library, which is odd, but I may have changed some components around. So obviously to fix that, I just want to get my resistor, which in this case was 100K. I need an R9, so I'm just going to change that. As you can see, this is just the warning, so we don't have to address it, but it's good to make sure that we are understanding why the warning happened. So I'm going to get rid of all the warnings for now and just concentrate on the errors. So we've got errors for our 5-volt pin. We basically fix it the same way we fixed this, and that's the same case for everything else. We basically need one pin that's driving that line. Obviously in the VBus case, there's not going to be anything that's driving it. It's just getting the voltage from the diode over here. So in that case, you can basically right click and exclude the violation. So it's basically ignored. Now over here, we've got some ERC errors, which basically say pins not connected. And these are very important. You don't want any errors that show you pins not connected. And in order to get rid of that, you can either connect the pin if that's what you needed to do. Or in this case, I need this pin to be not connected. So I'm going to put this flag over here, which says no connect, and tells the rule checker that we are intentionally not connecting these pins. So I want to go through each error and make sure I'm happy with it. Now you can leave the errors in as long as you know they exist and why they exist. So for example, I've got these errors here that say pins not connected, but I don't need those pins connected, so I can leave that error in if I wanted to. For sake of neatness, I'd rather put a no connect flag on them and get rid of the error, which basically makes it easier to see any other errors that you do actually want to find. So now you can see I've only got 3 errors and they are all related to the power lines, and I'm going to exclude all of them and we don't have any more errors. So now let's quickly have a look at the warnings. So we have some off-grid connections over here. That's probably because I copied and pasted this 4 times or 3 times over here to get this. Now we can put it back on the grid if you need to, if you're that concerned. If you're not concerned about it, then just leave it off. But it's a good idea to put things on the grid because sometimes not having things on the grid can hide errors like non-connections. Obviously we are running the ERC rule check, so it's going to be fine for that. So you can see I've got rid of all those errors just by kind of rearranging these slightly, and that's just for sake of neatness. I don't really care about them. And these, I think I changed my libraries around a little bit so they're not matching with some libraries, but I'm going to ignore that for the time being. Now, some other good things that ERC errors can give you is when you connect 2 inputs together. So as an example, let's have a look at this part over here, which I've drawn the symbol for. So I know I've drawn the symbol properly. So I'm going to put 2 of these parts down, zoom in so that you can see. I'm just going to add some flags so that it doesn't give me errors that I don't want to see. But let's say we connect the output to the output of this part. Obviously, you shouldn't do this in real life because you're connecting 2 outputs together and they're going to conflict. Now, if you run the ERC check on this, you can see that KiCAD has flagged that error and it's told you that you're connecting an output power pin to an output power pin. The same thing also works for like your logic pins. So let's say, for example, you have a part that has UART, RX and TX. I think we have a part like that on this schematic as well. So this part over here, which is the USB to serial converter. If I put another one down, so you can see if I configure this pin properly and label or configure this pin as an output, it will prevent me from connecting this TXD to this TXD, which obviously wouldn't work because you would want the TXD to connect to RXD and prevent that mismatch. Now, I don't know if this part has been set up properly or not because I've not drawn it, but it prevents those type of errors basically where you're connecting inputs and outputs together when they shouldn't be connected. So to summarize, always run an ERC check on your schematic just before you move on to the PCB design. There are a few more things I want to talk about. The one thing is assigning footprints. Now, the way I manage my libraries, which I'm going to make a video on at a later date, I don't need to assign footprints. So you can see all my components have a footprint already assigned. So if I click on anything, you can see a footprint is already assigned. But if you're using generic parts from KiCAD, so let's say we're using a resistor from KiCAD, so that's this device over here. Let's put that down so you can see that's R26. Now, as a default, this component will not have a footprint assigned, will not have a value assigned to it as well. So you need to assign those things before you move on to the PCB design. So to do that, you basically click on Assign Footprints over here. Let's find R26, which is down here. What you do is you go to the default resistors library. So let's say we're using a 0402 SMD resistor. You click on this component, you select your library, and you double click the resistor symbol from over here, and that's assigned the 0402 resistor symbol to this component, basically R26. Now you might have multiple components that don't have symbols, and you'd basically go into the default libraries for KiCAD, which has gotten a lot better recently, and there's symbols available for almost everything. There's footprints available for almost anything. But if the footprint is not available, or if the symbol is not available when you're creating your schematic, you'd have to create that yourself. So obviously assigning footprints is very important. And if you have any missing footprints, and when you transfer over to the PCB design side, which I'll show you now, so you can see I've got two symbols that don't have any footprints assigned. Now if I go into the PCB design side and I load in my components, you can see KiCAD has flagged an error telling me that two components don't have a footprint. Now it's very easy to miss this as well because there can be a ton of warnings and there's a ton of messages as well. And if you close that very quickly, you have missed that message. Obviously you don't want to do that. So assigning footprints is a critical step because obviously that tells the PCB side what footprint that component is going to have so that you can do your PCB design. Now if a footprint is missing and you've not realized when you're doing your PCB design, obviously that's going to be a major headache, especially if you've gone through the manufacturing and the assembly step as well. Now, the last thing I want to talk about is generating bill of materials. The bill of materials is a list of all the components used in this circuit, along with the quantities, values, and other relevant information such as supplier, manufacturer part number, supplier part number, the manufacturer itself. Now the BOM is essential for ordering the parts you'll need to build your PCB, or if you're doing a turnkey assembly, then you need to provide the BOM to the PCB manufacturer. So you need to make sure you get this right. A well-organized BOM will save you time and prevent errors when you're ordering your components. It's also useful for documentation and for anyone else who might need to understand or reproduce your circuit. So in order to generate a bill of materials, it's quite simple. You basically click this symbol here, which gives you this pop-up. Each one of your components will have a certain parameters that are associated with it. So if I give you an example, C7 over here, you can see C7 has a reference designator, has a value, footprint, datasheet, description, manufacturer, manufacturer part number, supplier, supplier part number, package. Now, if you're using the generic components from KiCAD, they typically won't have any of this information because you still need to find the right components and everything. I'm going to show you how I build my library in a different video. So you can have all your components basically like this, making it very easy to generate your bill of materials. If you don't have that, obviously, then you'd have to generate your bill of materials in a slightly different way. So what you can do is just assign values to all your generic components, and KiCAD will group that for you in here. So you basically click the BOM symbol, go to edit, and this shows you what your BOM is going to look like. The things that you need to include in your BOM typically is your reference designator, your quantities, your value, your manufacturer, manufacturer part number, supplier, supplier part number, and the footprint. You don't need the data sheet. I don't need this footprint because I manage it slightly differently. So I'm going to get rid of that footprint and I'm going to include the package. You can see that's a lot neater compared to the footprint. And I add this field when I create my component. I want manufacturer, manufacturer part number. I want supplier and supplier part number. You can see I've got a spelling mistake in one of my labels, so I need to correct that at some point. I'm just going to get rid of that. And you can see I've got my manufacturer part number. If you have any do not place components, obviously you want that on here as well. What you don't need is exclude from BOM. And what you don't need is exclude from board. So this is the type of information that you would need to supply to a PCB assembler in order to get your board built. So next, you basically assign a path and you click the export button, which will generate a CSV file for you that looks something like this. And this is basically ready to go to a supplier. So very easy to do if you manage your symbols appropriately. Before I forget, another thing that you want to do is add in your design notes to your schematic. Adding notes to your schematic is a great way to document your design. So you can add notes to explain specific circuit choices. So in this case, I've added a note why I've chosen a 1K3 resistor over here. You can highlight critical components. You can describe unusual aspects of the circuit. So this is invaluable when you come back to the design at a later stage, or if someone else needs to understand it. Now, if you're doing a design for the first time and it's not been fully proven to work, or it's going to basically need some testing in production, you should add test points to the circuit. Test points are locations on the circuit where you can easily measure the voltage and signals. They make it much easier to debug and test your PCB after it's been fabricated. To add a test point, there's an existing symbol that you can use. Basically go into your add a footprint, type in test point. You can see there are test points that you can add to the schematic. So if I just take this one, let's say I want to monitor the battery voltage, I can add it to the VBAT line. And what this will do is create a little circle on your PCB. So let's say we assign a footprint to it. Let me get one of my existing test points. It'll be easier to test on the PCB side. So let's say I add a test point. I go to my PCB. I import my symbols. And you can see I've got this circle over here that's connecting to my battery. And if I show you what that looks like on the 3D viewer, you've basically got this exposed piece of copper over here, which you can probe with a multimeter or a oscilloscope and see the value. So voltage, signal, you can connect it to anything. You can connect it to, let's say, your USB lines, your UART lines, your control lines for the transistors to make sure they're working. Basically anything you need to. Some common ones might be like your SDA, SCL lines to make sure the IMU is responding to what you're sending it from the microcontroller, or if you're sending it properly from the microcontroller as well. Some test points on your voltage lines to make sure it's all powered up properly. So they make it much easier for you to debug and test your PCB after it's been fabricated. So can save you a lot of time if something goes wrong with the PCB, or if you're developing the code for your PCB as well and you've run into some problems and you need to look at the hardware to make sure that it's not a hardware issue. Finally, and this is very important, save your schematic frequently. KiCAD saves your work automatically, but it's always a good idea to save manually as well. It's also good practice to use version control like Git to manage your design files. So this allows you to track changes, revert to previous versions, and collaborate with others. But when you get to a stage where you're going to send it to review, you should version the file then. So let's say I'm sending this design to someone else to review, or I'm going to basically fix the design and review it myself. I can call this draft 1, and then once draft 1 is reviewed, I can move on to draft 2 if something needs changing, or I can move on to the final version if I'm happy with it after the PCB design is done as well. So that wraps up the detailed guide. to finalizing your schematic in KiCAD. By following these steps, you can ensure your schematic is accurate, complete, and ready for the next stage, the PCB layout. Spending a little extra time on your schematic can save you a lot of time and frustration later on. So you don't want to find errors when you're almost through your PCB design. You especially don't want to find your errors after you've manufactured your board. In the next video, we'll take the finalized schematic and start laying out the PCB. So make sure to subscribe and stay tuned for that. If you found this video helpful, please give it a thumbs up and subscribe to the channel. And as always, if you have any questions, feel free to leave them in the comments below. Thanks for watching, and I'll see you in the next video.